All right, so today we're going to go through quiz 1 and then look at lab 7. Let's take a look at the first problem. And there it is. When that code runs, what does it output to the console? So if you just do an overview, look at it, you see just a single variable in there, I. And we initialize I to 1 as in the very first statement. And then we have a loop that depends on the value of I. And as long as I is less than 128, we execute the body of the loop, which means we run these two statements. And when we finish those two statements, we reevaluate the loop condition to see if we want to execute the body of the loop again. So we'll just walk through it here. I'll keep track of the state of our single variable here as we go through the algorithm. So we have I is 1, so I is less than 128. So we need to compute I plus 1 here, which is 2, and that's what we print. We print 2. We don't set I to 2, we just print 2. We're not setting I here. And but here we're setting I because we have assignment. And what are we setting I to? Well, we're setting I to the value of I itself times 2. So if I is 1, then 2 times 1 is 2, and so I becomes 2. Now we don't print anything, so you have to do this, one step at a time. And now that's the last statement in the body of the loop, so now we need to reevaluate the loop condition. The loop condition is still true, so we'll execute the body of the loop, compute I plus 1, and that's 3. And then we print 3. And we print a space too. And now we take what's I? Is I 3 or is I 2? That's the confusing part, right? So I now becomes 4. And the loop condition is true. So we print 4 plus 1, which is 5. So look at what's going on there. I mean, we could just do all of them. Or we could just see that each time we run the loop, we print I plus 1 and then we double I. So, I is originally 1, and then each time we double I, we get this. Oops. Finally, when we double I here, we get 128. So after doubling I, we check the loop condition, and if it's true, we print 1 more than what I is. So if I just look at the list there, do we print 129? No, because we don't get to here when I is 128, because that makes the loop condition false. So there's the answer for 1. Let's take a look at 2. It's like I can't fit it all in there. Suppose k is an integer variable. Write code that prints good when k is either positive or equal to -1, and bad otherwise. Now, a few people asked me whether 0 was positive, and 0 is not positive. And maybe I should have announced that to the class, actually, but that's the case. 0 is not positive. So let's write the code. So there's a k, so we compare k to we want to know if k is positive. So that means if k is bigger than 0, or if it's equal to 1, then we'll print bad. I'm sorry. We print good. I don't want those breaks. What's that? Oh, k is -1. Sorry, I'm thinking about something else. So we print good. God, let's print good here. So it looks like that. I'll try using Notepad. Yeah? A what statement? Oh yeah, I do. That's right. Thank you. I'm thinking about something else. Okay. So if k is greater than 0, or if k equals -1, then it's good. Else it's bad. Here it is. Okay.
What's the difference between that 4 and then the double and sign?
So this would be if k is greater than 0 and k equals 1. Is there such a k? Is there a k? Is there an integer that's both greater than 0 and equal? Well, there's only -1 satisfies this condition. -1 fails this. So there's no value of k for which both of those are true. So this is and. So you know this is this condition is evaluated first. That's either true or false. And this condition is evaluated next. That's either true or false. And so the whole expression will be true only if the left-hand side is true and the right-hand side is true. If either side of the logical and operation is false, then the whole statement is false, or the whole expression is false. Is that okay? All right, number 3, what does this code print when it runs? And looks like, I'm just glancing there, and I see there's 2 variables. So let's keep track of the state of those 2 variables as we work through the problem. In the first statement, we declare k, and we initialize it to 901, and then we initialize n to 0, and then we execute this loop. And notice that in the loop, k never changes. So k is always 901. So you could just mentally replace k with 901. And so if you start counting from 0, and when you reach 900, if you go from 0 to 900, suppose I reaches, so we increment I in each iteration of the loop. So we start at 0, and we do the body of the loop, which is here. And then we increment I, and then compare I to k. So when I reaches 900, the loop condition is true. So we execute this statement here. Once we, for 900, I'll say we have the I in there as well. Sorry about that. So we start with I is 0. And I reaches 900. Now if we started at 1 and we went to 900, we'd have, 900 numbers. But we're starting at 0, so we have 901 numbers implied here. So the number of numbers that are there are 901. So I takes on each one of those values. So the loop runs 901 times. And when I becomes 901, the loop condition fails. So this is it. I takes on these numbers only. But this statement doesn't depend on I. So it's just we want to run that statement 901 times. So if we start, if n is set to 0 and we add 1 into n 901 times, then n will become 901. So when we exit the loop, we'll print 901. Yeah.
Why doesn't it print every number between 1 and 901?
Because the output operator is not inside the body of the loop. So it's not repeated. Any other questions? Okay. All right, number 4. When the code in figure 3 runs, what does it output to the console? This is another problem where we simply need to keep track of the state of the variables. I mean, they're all basically keeping track of the state of the variables. So n is initialized to -1, and then we create k, and we initialize it to something. And you'll see here, this is the post increment, as opposed to the pre-increment, which appears in the third statement. So in the post increment, we delay the increment until we use the value, and then we increment later. So we just use n as it is, which is -1, multiply by 2, we get -2, and assign it into k. After we assign -2 into k, then we increment n. So now n becomes 0. See the 2 steps in that. Now this statement is complete. Now let's go to the next statement. When you look in there, you have to decide what to do first. There's 1, 2, 3, 4, 5 operations. Well, the output operation, we're going to do that last. It has the lowest precedence. That's done last. And the parentheses here mean that this operation, that modulo operation, will not be done until the expression inside the parentheses is evaluated. All right, so that means we have to evaluate the expression inside the parentheses. And of these operators, this increment, pre-increment operator, that has the highest precedence. And you can see it's expressed in the code. There's no space between the n and the plus plus. If multiplication had higher precedence, it might be perhaps better to write it like that, just to express that. That's why, spacing and the way you write your code is important for readability. It expresses things like that. So we're going to increment n first. So that means n becomes 1. And then we multiply the result by 16. So this whole expression evaluates to 16. And then we add 16 with -2, so we get 14. So this expression evaluates to 14. Now we take 14 and we divide by 4, and then take the remainder. So 3 4s is 12. Take that out of 14, we're left with 2. So 2 is the remainder. So we print 2. Maybe that's hard for you to follow because it's all written out in words. I mean, spoken in words. If we wanted to write it out, we could do something like this. Oops, 4. So we could say, well, if we increment, I have to go backwards. K was -2 and n was 0, right? We could start replacing the symbols. So n, if we increment n becomes 1. And we'll leave 16 alone. And k is -2. I'll just write it like that. So let's combine 1 times 16. Well, that's just 16. We can drop the plus. Plus -2 is I'll just do it like that. Plus -2. Now we get 14. And 14 is 12 plus 2. I don't know if this helps or not, but this is one way to do it. So 12 plus 2 modulo 4 is 12 modulo 4 plus 2 modulo 4, so that's division. It's a division. And then this will be 0. And remainder here is 2. That's another way to do it. If you wanted to write it out in steps.
So this isn't the one that prints up that percentage sign, the modulo. What would be the one that prints up the I guess the whole number? Like, I put 3.5.
What's that?
I put my answer 3.5.
3.5? No, it's 2.
I know that.
Yeah. Oh, so what was the question?
I'm saying when you do the percentage dividing.
No, that's not percentage. It's called modulo. Right. Okay. When you divide, you get a quotient and a remainder. You throw out the quotient. Take the remainder. So you wanted to throw out the 3 and keep the 5, the 0.5. But you would have to take 0.5 times 4 to give you the 2 back. Any other questions on that one? Okay. So what about this one? When the code runs, what does it output to the console? Let's go ahead and study examine the state of these variables as we walk through the code. I mean, actually, there's 2 ways of doing it. One, we could just walk through the code, or we can try to analyze the code and reason about it. In the last problem, we just walked through the code. We didn't reason about it. But with the code that where 901 was the answer, we reasoned about it. We didn't add 901 times. We ended up reasoning about the code and deducing the answer through our reasoning process. All right. So here we have a loop, and as long as the loop condition is that I is less than or equal to 999. And the body of the loop ends up modifying the value of I, which it has to do for a while loop, because if I didn't change in the while loop, if we entered the loop, we would have an infinite loop. So I has to change if we enter the loop. And once again, this this is what we're trying to do. We need to figure out, okay, when the loop stops running, what is I? Because that's what we're going to print. See, this print statement is outside of the body of the loop. So the problem here is to figure out what is I when we exit the loop. What is I when the loop condition is false? So let's see. When we first hit the loop, I is -1. And so the loop condition is true. So we'll add 200 to I. So now I becomes, I'll do it like this. I becomes $199. And then we compare 199 to 999. And that's 199 is less than 999, so we'll add 200. So that's 399. And we'll keep adding 200 until the loop condition is false. Is the loop condition false? No, the loop condition is true. Did I get that right? $11.99. So we exit the loop when I is $11.99. So that's what we print. Any questions on that one? All right, let's look at the next one. When this code runs, what does it output to the console? All right, there's a lot of variables in there. Let's keep track of those variables. I is 1. J is 2. And X, which is a double, and that's the key to the problem, is that X is a double, and I and J are integers. The purpose of this problem is to verify that you know the difference between integer division and floating point division. And here, the division I divided by j here involves the two operands in that operation are integers, and so the compiler interprets the division as integer division. An integer division does not return, it always returns a whole number. It returns an integer. So if we take I, which is 1, and divide by j, which is 2, we will get 0. It's not rounding, it's truncating. And so this evaluates to 0. Is 0 larger than 0? No. So the condition for the if statement is false. So we don't execute the body of the if statement. So we come down to the next expression here. Now x is a floating point value, and j is an integer. So the compiler interprets that as floating point division. That means the result will be a floating point number. We don't truncate. We don't lose the decimal point. We don't lose the fraction, the fractional component. Actually, what happens is I, behind the scenes, I, which is an integer, is converted to a floating point number. It's converted to a double precision floating point number to match the type of x. And so this will result in 0.5. And so this part of the expression evaluates to 0.5, and that is bigger than 0. And so we print beta. Any questions? Okay. When the code in figure 5 runs, what does it output to the console? let's create a variable I, initialize it to 2. And then we have a loop. And notice that the statement inside the body of the loop does not depend on the index that's used for a counter in the loop condition. So this statement, I equals I plus 2, is independent of k. So k is only used to count how many times the loop runs. And how many times does the loop run? If we start at 0 and we let k reach 499, as soon as k hits 500, we don't execute the body of the loop. I mean 500. So this loop runs how many times? 500 times. So we're going to add 2 to I 500 times. We're going to add 500 2s. 500 2s. 500 2s is 1,000. So we're going to end up adding 1,000 into I. But I started at 2. So the result will be 1,002. Any questions on that one? Write code that computes the sum of integers 100 through n, where n is an integer strictly greater than 100. You can use a for loop or a while loop. I'll show you how to do it with a for loop. We'll use a loop like an index I, and we'll start at 100. And as long as I is less than n, we'll increment I. So that's not quite what we want yet. It's just the first pass to getting one step here towards solution. So we have a loop. How many times do we want to run the loop? Well, we're going to have some kind of a variable to accumulate a value. There it is. Sum. Declare sum as an integer. We're working with integer numbers. We'll set it to 0. We're going to add. So we're going to do, we want sum to be 100 plus 101 plus 102 plus dot 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 plus n. That's what we want. This is the sum of integers 100 through n. So we set. So basically, we're going to have sum, and we're going to add this loop index I into it. So we want I to be 100 the first time around. That's because that's the beginning of our problem there. We're going to start with 100, and then we want to make sure that n gets added into sum. Is that loop okay, or do we need to change something? Does that loop end up adding n into sum? When I hits n, does n get added into sum? No. When I hits n, we exit the loop. So we need less than or equal to n. So this is the answer right here. This is just our, whoops, sorry about that. This is just part of our scratch work on the side. Any questions on this one? See, we need to do something repeatedly So when we need to do something repeatedly based on a value that we don't know in advance, we need a loop. If we knew n were 103, we would just do 100 plus 101 plus 102 plus 103 and we're done. But we don't know n in advance. It's some value. And we need a loop that depends on that value. We will need to repeat the operation based on a number of times based on that value. There is a formula, by the way, to get the answer without entering a loop. Yeah?
Question, please. So since we initialize I at 100 and it's always less than or equal to n, does that constrict n to be greater than 100 also?
That's right. That's why we say n is an integer strictly greater than 100. That's the reason I added that in there. So you can assume that n is, in fact, strictly greater than 100. That's part of the assumption when you solve the problem. That would be called a precondition. So when you write code, you have preconditions, or you may have preconditions. Now sometimes your code would check the precondition. So actually, maybe in production code, before we executed this code, we would test that if n was in fact less than or equal to 100, then we would abort the operation. The precondition has failed. Or maybe what we would do instead of that is we would simply use an assertion, and that's the style that we're using in this class, which is a common style. So you can express the precondition with an assertion, and in fact that's what you need to do in the labs and in the subsequent quizzes and final that we have. You need to use assertions to express things like preconditions. If this were to be false, this part of the code would not run. The program would terminate with an error message. All right, let's do 9. Write C++ code that prints every odd number between 100 and 1,000. Well, that's another loop. And I think this one is a little easier. If we start at 100 and go to 1,000, and then we'll print if the number is odd. So we can divide by 2. If we get 1 as a remainder, then let's print I. So, when I is 100, 100 mod 2 is 0, so it doesn't print 100. But at 101, 101 mod 2 is 1, so that expression is true, so we print 101. And so this loop is okay, because there are many different solutions to this. Here's another one. And we can start at 101 and stop at 999 and make that I less than or equal to. And instead of incrementing I, let's replace I by itself plus 2. Let me just stretch that out. And then we don't need this condition down here. There's an equivalent solution. Maybe this one is more efficient, performs less operations. It doesn't look at every value of I. It only looks at half the values. And there's other formulations as well. I think these are the two basic ones, though. Any question on this? Okay, write C++ code that prints 100 random integers where each integer is between 0 and 99 inclusive. That means include 0 and include 99 in the range. Hint, use the rand function with the modulo operator. So we do have a loop again. We want 100 random integers. So let's make a for loop that runs exactly 100 times. Start counting at 0 and stop at 100 without executing the loop. So we need to print, let's compute a random number. Let's compute a random number here, and then we'll print the random number. Other problem is, how do we calculate a random number, right? So we compute n 100 times, and we print that n. So if we use rand returns an integer between 0 and the largest possible integer. But we want to restrict the value to 0 to 99. And so the standard approach is to divide by 100 and take the remainder. So the random value that we get, modulo 100, will give us a remainder that's inclusively between 0 and 99. Any questions on that one? Does it seem easy now? So you can get, these are not that tough, so you can get all of these problems correct on the final. They'll all reappear again on the final in some variation of what is on this quiz. You just have to practice this. Okay, let's look at Lab 7. Oh, and there is assignment 2, by the way. So that's very important, assignment 2. And you should put a lot of energy into assignment 2. And I will not present the solution to assignment 2 until the deadline. And then after you submit assignment 2, I'll show everybody the solution. And then in the next in the next class, we'll have a quiz on this material. That's assignment 2. Let's look at Lab 7. And there are 3 exercises in Lab 7. Let's go through these. The first exercise is to implement a function that does something. And use assertions to validate the correctness of our implementation. And this function is an exercise with arrays. As you can see here, we have an array appearing as the first argument in this function. The name of the function is myMaximum. The purpose of this function is to determine the largest integer in an array and tell us what the largest integer is. So it returns it as the return value. So myMaximum has a return type of int. We pass in an array, we build an array A, however we get it, we have some A. we pass it into the function. Oh, we have to say how many elements are in A, because in C++ the language does not provide the length of an array if you just have a reference to the array. You have to separately keep track of the number of elements in the array. So the function takes two arguments. It takes a reference to the array, and it takes an integer, which is the number of elements in the array. And obviously we have a loop, so we're going to have to loop through the array. We have to look at each individual value in the array and figure out which one is the biggest and return that. Okay, so what is an array? And this is the syntax. It just says that A is an array, just like you could say that, number of elements is an int. Here we're saying that A is an array. So the syntax you have to get used to there. It's got those square brackets following the variable name, has the data type to the left of the variable name. And an array is a sequence of values. So we could have an array of double or an array of bool. But here we have an array of int. So this is a sequence of integers. How many integers are there? Well, if you just give me A and say it's a sequence of integers, I don't know how many are there. You have to tell me separately how many are there. That's why the function takes that second argument. Similar to arrays, you have vector. With a vector, you don't need to specify the number of elements in the vector. Vector is also a sequence of values. Just like an array, it's essentially an array. But it has built-in operations. It's, in fact, a vector is a class. It's got lots of operations that you can use that provide, which are a convenience to the programmer. And one of the things that a vector has is the number of elements that are in the vector. So we're going to look at both of those approaches to coding with sequences of values. And so here we have, let's go ahead and implement this. And use assertions to test the correctness of our code. I'll just copy main from somewhere else. Oh, that's not right. This is a function, so we have to declare it before we use it. So we have a function, my maximum. Actually, what I want to do is I'm going to implement my minimum, because I want you to do a little work in the lab. So there's a little bit of extra work to figure that out. Okay, so we're going to figure out the minimum rather than the maximum. And so we can call it here. We have an array. Let's see if I can remember how to do this. So we have values like this. I think that's the syntax. So we create an array, and then we call my minimum with the array, and the number of elements that are passed into it, which would be 5. Actually, I'm not sure of this syntax yet. I think that's one way to express it. Let's see if that builds. And my minimum returns the maximum value. So let's just go ahead and print that out. Oh, I'm sorry, the min. Let's see if that builds. Oh, it looks good. Ah, what happened there? Okay. So we pass in A. Oh, we're not doing anything. So the compiler actually didn't complain. It generated the compiler added some default return operation. Let's make that a better functioning stub. Whoops. I think the compiler in that case should have failed, and there's probably a setting that that we can use on the compiler, some switch, like strict or something like that. Oh, it took it. I don't know what it does. And there it is. The minimum value is 0. But that's not how we're going to test our function. We're going to use assertions. And if we pass through all the assertions without having a problem, then we'll print all tests passed. So all tests will look something like this. We'll assert that my minimum of a comma 5 is 0. That's our first test. I don't know what minus s does. I would take that out. And assertion is not declared in this scope. We need a header file for that. All tests passed. I need a new line there. It's too hard to read it. Let's build and run. All tests passed. Good. But actually, this should be a failed test, right? The minimum should be -2. So when we call my minimum on that array, we should get -2. That's the smallest value. So let's see if our test procedure is set up correctly. This should fail. This should abort. There it is. My minimum equals -2 failed. Okay, so we've got our testing framework in order. So how are we going to figure out the minimum value? So we're going to need a loop. We'll have to look at each number. So we'll have an index, and we'll start at 0, and we'll continue as long as the index is less than number of elements. We need to increment the index. And just to show you, this is not the solution. I just want to show you how we're just going to think about what we're doing here. This is how you access the value in the array. You use this notation. You use these square brackets. And this expression evaluates to the integer that's stored in position I. And the position numbers start at 0. So there's position 0, position 1, position 2, like that. So if there are, say, 3 elements, if the number of elements are 3, that means there are positions 0, 1, and 2. Position 3 would be an error. There is no position 3. There's 3 elements, but because we start counting from 0, the last position would be 2. And let's see what this should output our array, right? Let's see if we can get that to work. And I'll put this in there. That actually might not print the values, and I'll explain why if it doesn't. Then I can explain something more. Let's see if that works. It does work. So there's the contents of our array: 2, 7, minus 2, 11, and 3. So we're outputting that A of I. And then our test fails. Our assertion fails. Of course, that's not what we want to do. But we just wanted to understand how it is that we access each of the elements. And that is the notation right there. That's how we get at the element. So in here, we're going to have something like, we've got this element, and we want to know that, hey, is this thing less than the current minimum that I have? So we have, maybe we're going to keep track of what we think the minimum is. We can only look at one at a time. So let's assume that the first one is the minimum value. Let's assume that the first one is the minimum value, and then we'll look at all of the others. We'll assume the first one is a minimum value. And then we'll look at A1 through the end. So we don't need to re-examine the first position. We could start at 1 now. Let's assume that the one in position 0 is the minimum, and then we'll look at all the remaining numbers, and if we find one that's less than the minimum, then we've got a new candidate for the minimum. So first we would set the minimum to 2. Then we would look at 7. But 7 is not less than 2. Then we would arrive at minus 2. Minus 2 is less than 2. And so we would assign minus 2 into minimum. And then we would skip over the next 2, and we're done. And we're not going to want to return 0. We're going to want to return minimum. Now we pass the test. But there's a precondition here on that function. You know, if number of elements is 0, then this will be an illegal operation. So we could, in fact, put an assertion in for that. Well, it can't be negative either. That doesn't make sense. So we could just put that in there, just in case someone throws a bad number at us, and we can output the failed assertion, so it's easy to find the bug. All right. So now it's a matter of just generating the test cases. So there's an array A. Let's take another array, say B. This time we'll put the minimum on the end, and maybe we'll start at 0 and take a value out, something like that. This minimum value should be 3. And we're testing B. Let's test another array, say C. We'll put the minimum in the front. We'll make it a little shorter. This has got 5 values in it. This only has 3 values. This is array C. It also has 0 in the first spot. Let's test all the possible funny looking arrays that we can get. Let's suppose we had an array with 1 value in it. Does that work? Well, there we go. So there is the value here should be 7. Let's run our tests. Oh, failed assertion. Array C. Oh, this should be D. The problem is the test code, and that's in fact 1 element, not 7. My minimum D1, that fails. Oh, this should be 7, right? Actually, this is a point I made earlier about test code. You have to debug your test code. And there it is. Those are the tests. Any questions on arrays or this particular solution? Yeah.
For the assertion part, every time we say it equals a certain value, like on the last one we said 7, that's saying that's our minimum?
Yeah.
Okay.
In other words, 7, this is the left-hand side of the comparison operator. So this function should return 7, right? Because the array D has only 1 element in it. So we pass in this array D, my minimum better return 7. See what I have highlighted there, just mentally replace that with 7. That's what it should return. And this is 7 equals 7. Okay. All right. What about exercise 2 and 3? So 2 has uses vectors, and then it has this reference here. We need to talk about what that means. And then exercise 3 is a very good exercise to work on. Are we running out of time, or can we? Let's see, what is our schedule like here? So today's the 22nd, and assignment 2 is due on Monday, so we'll review assignment 2 on Monday, and then on Wednesday we have this, and then the Monday after that. So actually, we have quite a bit of time after this assignment 2 before we hit quiz 2. So I think we have time to get there, so we don't have to cram in the next 2 problems today. Any other questions? Okay, that's it then.